Once again, I welcome all of you to this section of Thermal Engineering, Mec551. Okay, so we already started this chapter last week, so we'll continue. Hopefully, we'll be able to complete it. Okay, last week, let us refresh our mind what we did. We did look at the various types of heat exchangers. We also mentioned that there are parallel flow. Parallel flow means that both the hot fluid and cold fluid are moving parallel to each other, the same direction. And then for counterflow heat exchanger, both fluids move in opposite direction. And the cross flow situation is that both fluids move perpendicular to each other. Okay, so we have also shell and tube heat exchangers. Okay, so today we're going to look more details about the thermal engineering aspect of heat exchangers. Okay, so here we have a parallel flow heat exchanger in which the fluid, okay, so we have a shell and then a tube. So this is a tube in which we have a warm fluid flowing into the shell and cold fluid entering the tube. Okay, so this is a parallel flow arrangement. Okay, and both fluids are moving in the same direction. Now, what we should know over here is that the temperature profile for such a flow or heat exchanger is given by this diagram. Okay, so if you look over here, initial temperature of the cold fluid is given by T cold in, and initial temperature of the hot fluid, TH in. So what happens is that as the cold fluid enters, it exchanges heat with the hot fluid. So the hot fluid transfers some amount of heat into the cold fluid. So its temperature increases gradually, asymptotically like this. Okay? And then that of the hot fluid, its temperature reduces gradually like this. Okay, so this is the temperature distribution, the temperature profile for a parallel flow heat exchanger situation. And for a counterflow means both fluids are moving in opposite direction. So now what we have over here is that in counterflow, this one is moving in this direction and the other one is moving in the opposite direction. So again, initially, the cold fluid, its temperature starts increasing, and then the hot fluid temperature starts reducing. Okay, so in this way. So that's the classical difference between the two. Okay, so for the cross flow situation, and we have noted that in cross flow situation, both fluids flows in what? In the opposite, perpendicular to each other. We have unmixed flow, and then we have the mixed flow situation. And here also we have the shell and tube heat exchanger. Okay, so these are example the way baffles have been placed, okay, and in order to ensure that the fluids move, okay, and so that there will be a turbulency, okay, in the fluid motion. Okay, so this enhances the heat transfer. Okay, so also over here we have shell and tube heat exchangers. So we have one shell, two tubes, again, two shell, four tubes heat exchanger. And this is a heat, so plate and frame heat exchanger. Okay, so important thing we need to know over here today is the overall heat transfer coefficient. Okay, so let us bring our mind back to thermal resistance. Thermal resistance. Okay, let us consider we have fluid flowing into this pipe. Okay, and then we have this an inner inside tube and this an outer tube. So also across this particular section, we have a cold fluid. Okay, so it means that there will be heat transfer from this hot fluid through this inner cylinder onto the cold fluid outside. You understand me? Okay, so the thermal resistance diagram for this situation is given by, we have convection in the fluid, the hot fluid. The mode of heat transfer from the fluid to the inner surface of this cylinder is given by convection. So which is this? So let's denote it Ri. That's the thermal resistance for that. And then the thermal resistance for the wall. Through the wall, we'll have conduction heat transfer. So let us denote that by R wall. And finally, across the outer surface of the inner cylinder. So our attention is focused on the inner cylinder and not more. So also, with regard to the outer surface of the cylinder and then the cold fluid, there will be the mode of heat transfer is going to be R convection. Okay, so now the total thermal resistance for this particular diagram is given by R total equals to 1 over Ri. So this is the Ri, that's the thermal resistance for the convection, and this for the R wall, and this is Ro. This is the Ro means the thermal resistance for the fluid, the cold fluid. Okay, that is surrounding the outer surface of the cylinder. And be careful, we are only interested in the cylinder which is inside this cylinder. We are not interested in this cylinder. Okay, so now we define a new term called overall heat transfer coefficient. So this we know from our previous lessons that heat transfer, okay, with respect to thermal resistance equals to delta T divided by R total. You understand me? So now we are equating this heat transfer, rate of heat transfer equals to UA times delta T. What is this U? U is what we call overall heat transfer coefficient. So anytime you want to find Q, if you know delta T divided by R total, you can get the value for Q, or you can use this also, this equation to determine the value for Q. Okay, if you know the overall heat transfer coefficient. Bear in mind, A is the area of the cylinder. Okay, so here, you see, so this is the inner area, and then we have the outer area of the cylinder. So this is very important for us to, yes, so the inner area of this cylinder is given by this, and then the outer surface area is pi dl. Okay. Now, again, this equation can be written in this form, that Q equals to UA delta T, and is equal to UI. UI is the overall heat transfer coefficient with respect to the inside. Okay, and this is UO is again the overall heat transfer coefficient with respect to the outer surface of the cylinder. Okay, and by this we can establish a relationship between R total and overall heat transfer coefficient. If we go back, we know over here Q equals to delta T divided by R total. And this is given by UA delta T. Now here delta T will cancel delta T out. So eventually we'll have 1 over R total equals to U times area. So what is U? U is nothing. It is given by 1 over R total times what? The area. So whenever you are talking about UI, then it is given by 1 over R total times AI. And similarly, if it is UO, then it will be 1 over R total times AO in this way. Okay? So that's what we have over here. So anytime you want to calculate the total thermal resistance, if you know the overall heat transfer coefficient and then the area, you can easily find the value for R total. Okay, similarly, now we're going to do some modification with this equation. So we know by definition that R wall, the thermal resistance for the wall means I'm talking about the thickness of the cylinder. So the mode of heat transfer is conduction. And then the R wall is given by, so here we have the inner radius, and then we have the outer radius, okay, like this. So this is R I, and this is RO in this way. So now it is nothing, it is log of the diameter, outer diameter divided by the inner diameter, divided by 2 pi KL. This we already derived, okay, in the previous lessons. Now this again, we can express, instead of diameter, we can use radius. Okay, so this and this are the same. Now we introduce new parameter. Say let T equals to the thickness, and thickness equals to RO minus RI. Thickness of the cylinder. Okay, so this cylinder, the thickness of this cylinder, this one. So its thickness is going to give me, diameter DO minus the inner diameter. So that's what we mean. So over here, I divide both top and down of this equation, okay, by the thickness. So I can go back to my previous equation, so then it will not be affecting it. So now what we do is that we represent this RO minus RI with T, and that T is this. Okay, then we bring this function, okay, down to divide 2 pi KL, and that is it. 2 pi, it will divide the whole of this. The whole of this come down to divide the RO minus RI 2 pi KL, and that is it. Okay, so we remove the KL, so that this K is that. Okay, so this equation is the same as that. Okay, so now again this equals to T divided by K times 1 over, now instead of radius, now we again shift back to area. You understand? So the surface area, outer surface area minus the inner surface area. Okay, so as long as radius is the only thing which changes, pi is constant, so the length is the same, so we can switch between the R and then the area in this way. Okay, so, and you see, if you multiply this 2 pi by RO, that gives us outer radius, outer area, surface area. Again, the 2 pi L times RI, that gives us, again, the inner surface area. So the same thing applies to this 2 pi L, 2 pi RO L. So again, like this, okay? So now, again, the whole of this equals to T divided by K. Then we represent the whole of this by AM. What is this AM? AM is what the log mean area. Okay, the log mean area. A is called the log mean area, and it is defined by this function. Okay, so now we want to write down the equation for UO. We have already known that UO equals to 1 over AO times the total thermal resistance. So this total thermal resistance is given by the whole of this denominator. This is total thermal resistance. Total R is this. So there's the same thing. So we have 1, our A is this, that's our A. So now, if I push this AO into this equation, so I have AO here, AO, then I have AO over here. So eventually, I have 1 over HI, AO divided by AI, and then T over K, AO divided by AM. Then this AO will cancel this AO. So then we'll have 1 over HO. So all raised to the power minus 1, because this is 1 over the whole of this function. Okay? So this corresponds to our UO. So now, again, let us do some manipulation to the AO divided by AM. That is this. We want to, again, we bring this out. Okay, so this is the same as 2 pi DOL divided by AM. AM is the log mean temperature. Sorry, log mean area. Okay, so that's the log mean area. That's the log mean area. And then if you rearrange this equation, again, eventually you'll get this. So in place of AO divided by AM in this equation, we are going to replace by this. So that is given by, you see, here we have our U now equals to, so here we have AM divided by AO has been replaced by the whole of this. Okay, so now plus 1 over HO, okay, raised to the power minus 1. Similarly, if you want to compute UI will give you the same result. Okay, so you multiply AI by the thermal resistance, you're going to get this result. All right, so now, eventually, what we want to state over here is that as, let's say, as T approaches 0. What is T? T is the thickness. Thickness of what? Cylinder. Okay. So as the thickness, so it means that if I have the cylinder like this, I have the cylinder like this. This is the inner radius, DI, and outer radius, outer diameter, DO. So we are interested in this thickness. Now, if this thickness is approaching 0, it means it's very, 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 very small. So this implies that DI will be equal to DO. So then that means that DO divided by DI will be equal to 1. You understand me? So if that is the case, now if we move back to this equation, then log of 1, again, is going to give us 0. So then the whole of this will be 0. The whole of this will be equal to 0. Then we will have 1 over here. So eventually the whole equation reduces to UI equals to 1 over HI plus 1 over HO, all raised to the power minus 1. And that's what we have over here. Okay, so this assumption is very, very, very essential. Okay, now let us look at this question. We are told that a hot oil is to be cooled in a double tube counterflow heat exchanger. The copper inner tubes have a diameter of 2 centimeters and negligible thickness. Now, the inner diameter of the outer tube is 3 centimeters. So the inner diameter is 3 centimeters. Okay, so water flows through the tube at 0.5 kilogram per second, and oil flows through the shell at 0.8 kilogram per second, taking the average temperature of the water and the oil to be 45 and 80 respectively, determine the overall heat transfer coefficient of this heat exchanger. So now we want to determine U equals to 1 over HI plus 1 over HO, all raised to the power minus 1. So HI is the heat transfer coefficient for the fluid, for the cold water. And HO is the heat transfer coefficient for the hot water, for the hot oil. Okay, so this is what we need to determine. So now, the basic assumption is that the thermal resistance of the inner tube is negligible. Okay, so the inside tube, because its thickness is very, 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 very thin, so it has no thermal resistance. Since the tube is highly conductive and its thickness is negligible. And then similarly, both oil and water flow are fully developed. Okay, so and then the properties of the oil and water are constant. Means the properties, the density, thermal conductivity, viscosity, all remains constant. So now we want to find the values for HI and HO. These are the two very important information we need to determine. So now this brings us again to the concept of Nusselt number. See, we define Nusselt number equals to HD divided by thermal conductivity. Okay, so if we know all these parameters, the hydraulic diameter, we know thermal conductivity, we know the value for NU, then we can determine the value for H. You understand me? So, but how do we determine H? First thing is that we need to know the type of non-normal empirical equation that we need to use. Okay, so it means we need to know the flow situation. Is it laminar flow? Is it turbulent flow? Then it means that we need to find our Reynolds number. You understand me? So Reynolds number equals to the velocity times the hydraulic diameter divided by kinematic viscosity. Okay, so but all these parameters, kinematic viscosity, density, thermal conductivity, can be determined if you know the temperature of the fluid. So here we know the temperature of water. So it means the density of water is this, Prandtl number, thermal conductivity, and then kinematic viscosity are already given. And then for the second fluid also, at these temperatures, these are the thermal properties of the fluid. Okay, so, but here, one thing you should know is that we don't know the velocity of the fluids. Okay, so we need to estimate them. We only know the mass flow rate. You see, in the question, we only know mass flow rate of the fluid. So how do we determine the velocity? Because we need to know the velocity to determine the value for RE. You understand? So by definition, since velocity equals to mass flow rate divided by density times area, so classically, density, I'll show you how this equation is being derived. So density equals to mass divided by volume. For you, I think you know these equations already, very familiar. So volume equals to, that gives us, mass now gives us rho times volume. Now I can express this again. This is rho area times length. Area times length is the same as volume. Now I want to express this in terms of mass flow rate, not mass. So I divide this by time, I divide this by time. So now this gives me mass flow rate equals to rho A times L divided by time. Okay, rate of change of distance per unit time is velocity. So that gives us the V. Okay, so now in order to determine the velocity of our fluid equals to mass flow rate divided by rho times area. Okay, so here we have this equation. Now, the area, be careful over here. This area is calculated with respect to the, see, if you have the tube like this. Okay. Now, we are told that the hydraulic diameter is given by this. Okay, so hydraulic diameter, this is this. Hydraulic diameter is represented by HDH. So hydraulic diameter is the diameter of the pipe in which the fluid covers. You understand? So if you want to find the portion of the pipe that is covered by the fluid, it is this surface area. Okay, this surface area. And that's the area of a circle. And the area of a circle is pi d squared divided by 4. You understand me? Okay, so that's the area of the circle. So now we introduce that area over here, and we have mass flow rate density. So pi d squared, okay, divided by 4, that's the area. And if you substitute all the parameters, you get 1.61 meters per second. So now we calculate the Reynolds number. That's the velocity, hydraulic diameter, divided by kinematic viscosity. So this is our Reynolds number. So now, Reynolds number is greater than the critical Reynolds number. So it means the flow is turbulent flow. Okay? So now for a turbulent flow situation, the Nodson number, appropriate Nodson number to use is this equation. So you calculate this value, then equate it to this is a generic formula. So generally, Nodson number is given by H D divided by K for a pipe. And for a plate, NU equals to HL divided by K. This is for a plate, and this is for a pipe. It can also be for a sphere, so like this. Okay, so now if you calculate, this is the Nodson number. Now we use this to find the value for H, so it means H for the water is this. So similar thing has to be done for the hot oil. So in the hot oil, we have again, we need to find the velocity of the oil is the mass flow rate divided by rho times the area of that is covered by the oil. Now we will discover that the hydraulic diameter of the oil, yes, is given by this. So we are interested in that portion where the oil covers. So this section. Okay. So it is given by this diameter, the total diameter minus, this diameter minus the diameter of the tube. You understand? So that gives us that portion, that area. So now we will have DO minus DI. So that gives us 0.1. Okay, so it is this 0.1 that we will use to determine this area. You understand me? So area C equals to pi D squared divided by 4. You understand me? So that's the hydraulic diameter for the shell. Alternatively, you can also calculate that it is also equal to AO minus AI. You understand me? So AO, again, for that particular surface area, that will give us 1 over 4 pi D, DO squared minus DI squared. Okay, you get the same result. Either you substitute directly 0.01 into this equation, then you find the AC, or you do the solution in this way. You get the same result like this. So now we know the velocity of the oil. Now let us determine the Reynolds number. Reynolds number equals to 637. So this is laminar flow because the value is less than the critical Reynolds number. So eventually what happens, we will determine the appropriate Nodson number for laminar flow. And if you go to the textbook, for a diameter of this ratio, DI divided by DO equals to 0.667, we discover that the Nodson number to be used is 5.45. So this is what we'll use to determine HO, H for the oil. So eventually this is the value. So overall heat transfer coefficient is nothing equals to 1 over 1 over HI plus 1 over HO, and this is the solution. Okay, so quickly, let us move ahead. Now, we want to talk about fouling, effect of fouling. What is fouling? Fouling is the deposition of, let's say, micro or let's say small particles that are mixed in the water. So as you operate or use the pipe for a very long time, these particles will get stuck or deposited on the surface of the pipe, and it will form this thickness. You understand me? So assuming you have a pipe like this, and all the time fluid is flowing inside the pipe, and it could be also flowing outside the pipe, because we will be talking about a heat exchanger, okay, where we have cold fluid either flowing in this direction, hot fluid flowing in the opposite direction. So as time goes on, there will be some small particles that will be formed, they will be coated on the surface of the tube, as well as the outer surface of the tube. And these are what we call fouling. This fouling, what they do is that they increase the thermal resistance of the cylinder or the tube, okay, because they resist the heat transfer from the hot fluid to the cold fluid. So if we represent the fouling, the thermal resistance offered by the fouling by RF. So now let us determine this RF. Okay, so we introduce this RF into the equation. So we say if we define the fouling factors on the inside and then the outside surface to be RFI plus and then RFO respectively, then the total thermal resistance with fouling and then the overall heat transfer coefficient is given by this. Okay, so now eventually this is the fouling for the inside and this is the fouling for the outside. This is RI, okay, this is RFI, this is R wall, this is RFO, and that is RO. Okay, so the total thermal resistance is Ri, RFI plus R wall plus RO plus RFO plus RO. So that's the total thermal resistance. Okay, so now if you want to determine the value for UO, so what is this UO? UO we know is equals to 1 over H, okay, HO, oh sorry, divided H times, and that gives us area. So we have the area over here, okay, so that again here we have, oh sorry, this is R, I'm very sorry, this is total resistance. So total resistance times the area AO. Okay, so we want to determine UO. So that's a mistake over here. So 1 over R. So it means if we know the total thermal resistance, which is this, we just multiply the whole of this equation by AO. So then the resulting equation is this. Okay, so now where generally UO is low for fluid with low thermal conductivity values. And it is true, if you have a fluid with a very low thermal conductivity, such as gas or oil, then the value for U is very low as well. Okay, so let us look at this question. Here we are told that a double pipe tube heat exchanger is constructed of stainless steel tube with inner diameter and 1.5 centimeters and outer diameter 1.9 centimeters and an outer shell of inner diameter 3.2 centimeters. Now for the convection values and fouling factors, so here we have fouling at the outer surface of this tube, and similarly there is fouling at the inner surface of the tube. Okay, so the effect of value need to be considered. Now, we want to determine the thermal resistance of the heat exchanger. Okay, and heat transfer coefficient, UI and UO. So now, we will determine the, what do you call it? The surface area. So the surface area of the cylinder, inner surface of the cylinder is this. The outer surface of the cylinder is also given by this. So now, if we have to determine the total thermal resistance equals to 1 over the overall heat transfer coefficient and the surface area of the heat exchanger. So we can calculate with respect to the inner surface area of the cylinder or outer surface area of the cylinder, whichever way it's going to be the same. Okay, so now this gives us our R is given by the whole of this equation. These are the fouling factors for the inner and then the outer. Okay, so now if we substitute all the parameters, HI, AI, okay, and then AO, HO, RFO, RFI into the equation, eventually our total thermal resistance is given by this. Okay, so now we need to determine also UI and UO. So similarly, since we know the total thermal resistance, we just multiply by the inner surface area. And UI is this, UO is also given by that. Okay, so quickly let us move on to log mean temperature. So this is a different method. So now we have recognized that whenever you want to find the heat transfer through a heat exchanger, it is given by delta T divided by R total, which is equals to UA times delta T. Okay, so this is a very important equation, especially Q equals to UA times delta T. Understand? So that if you know U, which is the overall heat transfer coefficient, you know the value for A, the delta T, you can easily find the rate of heat transfer. So we want to use a different method for calculating this value. Okay, and this is what we call the log mean temperature difference. Now, let us consider again a counterflow heat exchanger. Counterflow means that the cold fluid is moving in this direction, hot fluid is moving in the opposite direction. Now, if both fluids have the same specific heat capacity, both fluids have the same specific heat capacity, means the specific heat capacity for the cold fluid is the same as the specific heat capacity for the hot fluid. Then we are going to have a situation like this, where the temperature difference at any particular point, you see, here, the hot fluid is entering in this section, and the cold fluid is leaving from this section. If you find a difference between their temperature, it is going to give you delta T1. And similarly, at any particular point, let's say at this point, you know the temperature over here to be T hot, and you know the temperature over here to be T cold. If you find the delta T, it is going to give you this. The difference between them means TH minus T cold is going to give us delta T. Similarly, if you determine the temperature over here, and then the temperature over here, you find the difference is going to give you delta T. However, this delta T is the same as delta T1 equals to delta T2, and this is a constant. And this constant is as a result of what? The same specific heat capacity. You understand? So that now, if we want to determine how much energy is gained by the cold fluid and how much energy is lost by the hot fluid, okay, we establish our energy balance. And the thing is that the amount of energy which is released by QH equals to the amount of energy gained by the amount of energy which is gained by the cold fluid. You understand me? So that is why we say that QH equals to QC. You understand me? As far as energy balance is concerned, so it is give and take. So I lose 10 ringgit and then you gain 10 ringgit. You understand me? So that's the concept over here. So the same amount of energy lost by the hot fluid should be equivalent to the amount of energy gained by the cold fluid, so that we establish the amount of heat gain by the cold fluid is nothing. It is the mass flow rate of the fluid times the specific heat capacity at constant pressure times what? Delta T. And what is this delta T? It is T for cold minus T for the, so T for the cold out, that's the temperature of the cold outlet, T cold out, minus temperature for the cold inlet in this way. So that's our delta T over here. And similarly, the heat gain by the hot fluid equals to the mass flow rate times the specific heat capacity. How does this equation come about? Now let us see carefully over here. So if we look carefully, let's say if I have a fluid, assuming that I have a fluid whose initial temperature is T1, if I transfer some amount of heat to it, say Q in, and let the mass of the fluid be M. Now, the rate of, or the amount of heat transfer into this system is always proportional to the mass. It means more mass, more energy. Less mass, less energy. You understand me? Okay, so, and it is also proportional to the delta T. And this temperature increases from T1 to T2. You understand me? So it means high temperature difference is going to give us more Q in. You understand? So now if we want to remove this proportionality sign, then we will put a new constant. And this new constant, we name it Cp. So this gives me M Cp times delta T. And Cp is the specific heat capacity at constant pressure. So now be careful. The unit for this is in kilojoules. So if you want to express this in terms of mass flow, assuming the fluid is flowing, you understand me? For example, in a heat exchanger, then we are going to divide this by time. We divide this by time. Then eventually we'll have Q dot rate of heat transfer equals to M dot Cp times delta T. And this unit is in kilowatt. You understand me? So this equation is similar to this. Whenever you have a fluid flowing, okay, it is exchanging heat, okay, with another fluid. The amount of energy gained by that fluid is the mass flow rate of the fluid specific heat capacity times the temperature difference. Okay, so now let us see. We want to simplify this equation, okay, by knowing that we define a new term called heat capacity rate. Heat capacity rate is equal to, so let's say originally we have told that QC equals to MCP times delta T. I'll say delta T over here. So my delta T is delta T out minus delta T in. Sorry, my delta T is T for the code out minus T for the code in. Okay, so now let's say we want to represent this by a unique parameter. Okay, so like we name it heat capacity rate. And this heat capacity rate can be defined as Cc equals to mass flow rate of the cold fluid times the specific heat capacity of the cold fluid. Okay, so now again, another term, capacity ratio. Capacity ratio is the ratio of the minimum heat capacity divided by the maximum heat capacity. Okay, so for example, if we do our calculation and then we discover that, let's say, if we discover that this equivalent to 5 and this equals to, let's say, 10, then this will be the C minimum and this will be C maximum. Okay, so then the capacity ratio will give us 5 divided by 10, which is about 0.5. Okay, which is 0.5. So that's the capacity ratio. Okay, so now we are saying that the temperature difference between the hot and cold fluid varies with distance along the heat exchanger. Therefore, it is convenient to use a mean temperature difference, okay, between the hot and then the cold fluid, so that Q, so you see, all along we have been talking about Q equals to UA times delta T. This equation is only valid for a situation where we have, let's say, a graph like this. So let's say this is the cold fluid, this is the hot fluid, and this delta T1, let's say, and this is delta T, and this is delta T2. This equation is only valid for a situation like this, like delta T equals to delta T1 equals to delta T2. And again, it is only valid when the specific heat capacity, okay, the CP for the cold is the same as the specific heat capacity for the hot. So if CP for the cold is not equal to specific heat capacity for the hot, then again, we will have a situation like this. We will have a situation like this. There will be a situation where we will have, let's say, this will be going like this, and then we will have a situation like this. So you see that at any particular point, let's say if you take this to be your delta T1 and this delta T2 and this, let's say, you can say delta T3, these deltas are not the same. So it means we cannot use this equation. So which one are you going to use? Are you going to use delta T1 to calculate this or delta T2? So this brings us to the concept of log mean temperature difference. So we need to use this equation. Or in other words, we are going to modify this equation by saying that we will now calculate Q equals to UA times delta Tm. And this delta Tm is defined as delta T1 minus delta T2 divided by log of delta T1 minus delta divided by delta T2. So now let us see how this is calculated. So a typical example is what I've given again here. Here we have a parallel flow situation. Parallel flow situation means the cold fluid is increasing like this, and then the hot fluid is decreasing in this way. So delta T1 is this temperature difference. Okay, delta T1, you see, is defined as hot inlet minus cold inlet. Okay, and then delta T2 is hot outlet minus cold outlet. Okay, so, and again, so now our delta Tm is defined as delta T1 minus delta T2 divided by log of delta T1 divided by delta T2. So now the modification of that equation, Q equals to UA delta T, okay, is now given by this. So this is for a situation where Cp for the hot is not equal to Cp for the cold. You understand me? Okay, so now let us see again. Yes, so for a parallel flow, a counter flow situation, I've explained to you already. Here, the delta T1 is equal to T hot inlet minus T cold outlet. Be careful over here. So here we have T hot inlet minus T hot outlet. And then again, we have T hot outlet minus T cold inlet. That's our delta T1 and delta T2. Okay, so then again, it is defined in this way. Okay. So now, let us see. Now, this equation can be written in any form. We can also write delta T in this way, that delta Tm equals to, very important, a student asked me this question, that's what I'm explaining. Delta Tm can be written as delta T2 minus delta T1 divided by log of delta T2 divided by delta T1. It is the same. You understand me? So the only thing is that if you start with delta T1, for example, this minus delta T2, then immediately delta T1 should come again at the numerator part of this, divided by delta T2. You understand? Similarly, if you start with delta T2 minus delta T1, then over here again, the first thing that has to come at the numerator part should be delta T2 divided by delta T1. Don't tell like this that this Tm is the same as, let's say, delta T2 minus delta T1 divided by delta T1 divided by delta T2. No, this is wrong. You understand me? This is wrong. Okay, so whichever way, this equation and this equation are the same. Okay, so that's why over here you see the delta Tm has been changed to this. So delta T2 minus delta T1 divided by, again, delta T2 divided by delta T1. Okay, so now we have both parallel flow and counter flow heat exchanger. How to determine their delta T? So delta T1 is given by this, T hot inlet minus T cold inlet. And delta T2 is also given by this. And similarly for the counter flow part, delta T1 is T hot inlet minus T cold outlet. And this delta T2 as well. Okay. So now here we have heat transfer between two fluids, a hot one and a cold one. But the temperature of one of them is maintained constant. You see over here. So the fluid temperature over here is constant all the way. It doesn't change, even though it is continuously transferring some heat to the cold fluid. You understand me? And this situation is what we call condensation. You understand? Condensation is the temperature of the cold fluid will be increasing, whereas the temperature of the hot fluid will remain the same. So it implies that, let's say, for example, if I have a fluid, okay, that is liquid vapor mixture, a saturated liquid let's say I have a fluid. Okay, so this is the liquid. I'll use this color. So this is the liquid. And then I have the vapor. And this is the vapor. Okay, so this is saturated liquid vapor mixture. Okay, let's say this is water. Now, you know the boiling point of water, temperature equals to 100 degrees Celsius, pressure is 1 atmospheric pressure. Now, if I put this whole thing inside water whose temperature, I drop the whole thing inside water whose temperature is given by 20 degrees Celsius. What will happen to this water? There will be heat transfer. There will be heat transfer from the saturated liquid vapor mixture into the cold water. And gradually you'll see that the temperature of the cold water will be increasing. But one thing you know is that the temperature for this saturated liquid vapor mixture is going to remain constant. The temperature is not going to change because of the fact that it is what do you call it? It has two phases. Whenever you have a two phase, if the fluid is undergoing a change of state, so the temperature remains same, pressure also remains the same. This is what we call condensation. And not until all the vapor has been condensed into liquid, temperature will never change. For example, if you look on our, let's say, TV diagram, on a TV diagram such as this, so there is a constant pressure line. Okay, this region corresponds to saturated liquid vapor mixture. Okay, so as you continue to, let's say, if you have a fluid over here, let me sketch it well so you see. So here we have a TV diagram. So you have a fluid in this region. So this corresponds to, this is the temperature. Okay, so if our fluid is in this state, temperature is 100, pressure is 1 atm. Okay, now we put this in a cold fluid. Heat will be transferred to the cold fluid, but then the temperature of this fluid remains the same, and this is what called the saturation, saturation temperature. You understand me? So this process is referred to as condensation. Now, similarly, we can have a boiling situation over here. Okay, a boiling situation where the temperature of the boiling remains constant, whereas the temperature of the hot fluid will be reducing. Okay, so this is for a situation where you have, let's say, superheated, temperature equals to 300 degrees Celsius, pressure equals to 1 atm. Okay, assuming this is superheated. Okay, so in superheated, if you dip the whole of this again into a container, okay, that consists of, let's say, water, whose temperature equals to 100 degrees Celsius, and pressure equals to 1 atmospheric. So this is a boiling water. Boiling water. So directly there will be heat transfer from the superheated fluid to the boiling water. So the temperature of this boiling water will remain the same because there is more liquid. So we'll have a constant line like this. But at the superheated state, temperature of the superheated fluid will be decreasing in this way. Okay? So now let us see in this equation where we have Q equals to UA delta T M. So now we have recognized that this is applicable for a situation where Cp cold is not equal to Cp what? Hot. Okay. Now this equation is valid only for a parallel flow and counter flow, strictly limited to single pass. Single pass means this equation is only valid for these two types of geometry. Okay, so it means if I want to find any heat transfer for geometries like this. So I would simply use Q equals to UA delta T M. But what about if you have two shell or two tubes, four tubes, and so on like this? So now we need to introduce a new parameter called the correction factor. So this correction factor is going to be generally used for all different types of heat exchanger, for counter flow, paraflow, to multiple pass, cross flow situations like this. You understand? So we are saying, however, similar relation are also developed for cross flow and multi-pass shell tube heat exchanger. But these are very complicated expressions. So now we just introduced a new term called correction factor. Okay, we introduce it to the LMTD. So now, how does this correction factor works? We use normally a graph, and on this graph, I'll come back to the previous slide later on. So we introduce a new parameter called F. And how do we determine this F? We use graphical information. Okay, so on this graph, for example, on the vertical scale, we have correction factor. Horizontal scale, we define a parameter called P. P equals to T2 minus T1 divided by T1 minus T1. And what is this T? Small t is that, small T1 is the temperature for the tube inlet, and T2 is the temperature for the tube outlet. And big T is the temperature for the shell inlet divided, and then again, T2 is the temperature for the shell outlet. So if you find all these parameters, if you know these quantities, T1, small T1, small T2, big T1, big T2, you substitute into this equation, then you can get the value for P. You understand me? So now, similarly, R can be calculated using this equation. So the value for R equals to T1, big T1 minus big T2 divided by small T2 minus small T1. Okay, so for example, assuming you get the value for R to be equal to about, let's say, 1.5, and then they get the value for P for about, P equals to about 0.5. Okay, so no, let's say we get about 0.4. I'll say just to make it easy for everybody. So let's say this is about 0.4. So clearly we will look to this particular graph or the horizontal scale. So our 0.4 is here. This is 0.4. And then 0.5 corresponds to this. So clearly we will move vertically upwards like this. Where it touches this line, then we'll move to the left. So this means our correction factor F will be equal to 0.8. And this corresponds to P equals to 0.4 and R equals to 1.5. So then you introduce this correction factor. Okay, so this is how to calculate our, what do you call it? P and then the R. Now, same thing can be done for, here we have two shell, four tubes. Okay, the same situation. And then we have cross flow heat exchanger also. Okay, so let us look at this question. So in any case, I need to finish this slide, inshallah, before we leave today. So be a bit patient. So here we have alcohol is to be cooled at a rate of 0.2 kilogram per second. Okay, from 75 degrees to 35 in a counterflow heat exchanger. Cooling water enters the heat exchanger. So this is the temperature of the cooling water, and then the flow rate is this. The convective coefficient between alcohol and the tube wall, and water is 0.34. Okay, so and then between the tube wall and water is this. So here we are giving HO and HI. Okay, so now the tube may be assumed to be thin. So if the tube is thin, then it means overall heat transfer coefficient is 1 over HI plus 1 over HO. 4 raised to the power minus 1. Okay, so that's, and then the specific heat for the alcohol is this, and specific heat for the water. So what do you observe over here? Here the CPs for the cold is not equal to CP for the hot. So it means you cannot directly use this equation and tell like this: Q equals to UA times delta T. You cannot use this one. You understand? Because the specific capacities are not the same. So all that we need to use, we have to use delta T M. So it means we have to calculate our delta T M. And this is given by either delta T2 minus delta T1, okay, divided by log of delta T2 divided by delta T1, okay, in this way. So now, this is the situation, the flow situation. HI is given, HO is given, okay. So now we have a counter flow situation. So you see, this delta T2 and delta T1, they are not the same, okay. So now, we know temperature for the hot inlet, temperature for the hot outlet is given. Now the cold inlet is given, but we don't know this one. So how do we determine this temperature? Now we need to go to, by following the energy balance. We say Q for the hot inlet equals to Q for the cold out, Q for the hot, that's the heat loss by the hot fluid, equals to the heat gain by the cold fluid. You understand me? So where we have Q for the hot equals to mass flow rate for the hot, and then we have the Cp for the hot times the delta T. So delta T means temperature for the hot inlet minus temperature for the hot outlet. Okay, so similarly, QC equals to MC CPC, and then temperature for the cold outlet minus temperature for the cold inlet. Okay, so then you equate these two. So if you know MH, CPH, you know MC, CPC, you know temperature for the only unknown is this quantity, so which you can easily calculate from this equation. Okay, so now let us see our capacity ratio. Before we calculate our capacity ratio, we have to calculate the heat capacity. Heat capacity for the cold is this, hot is this, for the cold is also given by this. So now this is the C minimum. This equals to C minimum, and C maximum is this. So the capacity ratio equals to C minimum divided by C maximum, which is this. Okay, so now the heat gain by the cold fluid equals to heat loss by the hot fluid. So we can express in terms of this. So you see, the only thing unknown is T, temperature for the cold outlet. So now we can calculate this to be that. Then by definition, the effectiveness, when we say effectiveness, is the same as, let's say, performance or efficiency of the heat exchanger. It is the ratio of the amount of heat transfer by the heat exchanger divided by the maximum possible amount of heat transfer. And this Q maximum is estimated according to C minimum times TH for the hot inlet minus T temperature for the cold inlet. Okay, in other words, it is the C minimum. What is C minimum? The C minimum is the minimum value for this, where we have already calculated. So here the C minimum is the heat capacity for the hot fluid. You understand? And then here you have to look which one has the highest temperature in the system. The highest temperature in the system is TH in. And the lowest temperature in the system, again, is T cold inlet. You understand me? So the difference between these two times the specific gives us Q maximum. Okay, so the ratio of these two gives us the performance of the or effectiveness of the heat exchanger. So now the temperature difference, that's the LMTD, can be calculated using this equation. Okay, so I've told you you can either use delta T1 minus delta T2, okay, divided by delta T1 divided by delta T2. Okay, so whichever way you use, you get the same result. So now we just substitute, we'll find our U equals to this, we know HO already. So now the surface area of the heat exchanger is calculated using this equation. Okay, so now that is it. Now, similar question, let us see. We will discuss this question also quickly. So I would like to finish this slide in anyhow, inshallah. So here we have cooling water at specific capacity flows through a 2-shell pass, 4-tube pass heat exchanger. So here, how many? We have 2 shell, 4 tubes. Okay? So similarly, first thing that has to come to your mind, Q equals to UA times delta T. Okay? So this equation cannot be used. Again, Q equals to UA delta T, delta TM. Again, this equation cannot be used. Because of what? Here CP for the cold is not the same as CP for the hot. Okay? Similarly, over here, we have 2 shell and 4 tubes. Because of that, we cannot use this equation. So the appropriate equation, which is good for this, HQ equals to F, correction factor, times the area, times delta Tm. You understand me? So this is the only way we can use to determine when we have 2 shell, 4 tubes, okay, 1 shell, 4 tubes, or whatever it is. Okay, so let us proceed. Here we know we have 2 shell over here, so it means we need to find a value for F. If we have to find F, then we need to know the value for P, we need to know the value for R. Then from the graph, we can find a value for F. Okay, so here, all the temperatures, inlet, exit of the heat exchanger are already given. So delta T is given by delta T1 minus delta T2, so that gives us 64.9 degrees Celsius. Okay, so now we need to determine our correction factor. Okay, so correction factor equals to 0.5 P, 0.833, that is equal to R. So now we move to the graph. So our R, okay, corresponds to 0.833, almost approximately 0.8. And then our P corresponds to 0.5. Okay, so eventually you move to the left, then our correction factor is about 0.97. So in this way, we substitute the value for F into the equation. So we know MC, we know CP, we know all these temperatures. We can easily calculate the heat exchanger area. So this is the result for the heat exchanger area. So the last section for this particular slide is the NTU method. NTU method is very, very, very important. Okay, so the NTU method is also another method which is used to determine the effectiveness of the heat exchanger. Now, let us see. I've already explained to you this epsilon. Okay, so the heat transfer effectiveness, you can say performance of the heat exchanger or efficiency. So in a loose term, we don't say efficiency of a heat exchanger. Okay, just as we have refrigeration, we cannot say, oh, what is the efficiency of a refrigeration system? But instead, the performance of a refrigerator is based on coefficient of performance, COP. So when we come to refrigeration cycle, then we'll understand all this concept. So here the same thing, the effectiveness of the heat exchanger equals to the actual amount of heat transfer rate divided by the maximum possible amount of heat transfer. You understand me? So this actual amount of heat transfer can be calculated by means of the cold fluid. That's the amount of energy absorbed by the cold fluid, or the energy released by the hot fluid. You understand me? And the maximum possible heat transfer, this Q maximum, can be calculated, okay, from Q equals to, I've told you, C minimum into bracket, the maximum temperature in the cycle, the maximum temperature. And maximum temperature can only be gotten from the hot fluid, so which is TH in. And the minimum temperature in the system is from T cold in. So this minus T cold in, like this. So this is how we calculate Q maximum. Okay? So now our capacity ratio can also be determined. If CH is greater than CC, then we use this. So it means this will be C maximum, and this is C minimum. Similarly, if, let's say, this is C maximum, and this is C minimum, then we use this equation. And this is also for this equation. So depending on which situation is maximum or minimum. So you see, the maximum temperature difference possible in the heat exchanger is given by this. And this is what we use to calculate Q maximum. Q maximum equals to C minimum, okay? C minimum times the delta T maximum. Yes, delta T maximum. Like this. Okay, so this is it. So the same thing I've told you. The maximum temperature in the cycle is this, and minimum temperature in the cycle is this. Now, effectiveness can thus be either using the cold fluid or the hot fluid, can be calculated in this way. So now, the NTU is a measure of physical size of the heat exchanger. So the significance of the NTU is it tells you about the size of the heat exchanger. Okay, for example, if you go to the market and they tell you that there are different types of heat exchangers, and you want to buy a heat exchanger whose NTU, okay, or number of heat transfer units equals to 0.5, and then another one is about 10, or let's say 0.8, then you should know clearly the one with 0.8 is going to be a bigger heat exchanger. So the significance of this NTU tells us it's a measure of the size of the heat exchanger. Okay, so it is clearly defined as NTU equals to the surface area of the heat exchanger times the overall heat transfer coefficient divided by C minimum. So this is the only definition associated with this NTU. Classically, the numerical, or let's say the theoretical definition is like this. So you see, it is even proportional to the area. Higher area, higher NTU. Lower area, lower NTU, in this way. Okay? So that determination of C minimum, C maximum, okay, can be determined from this capacity ratio. And so NTU again is defined like this. So effectiveness of the heat exchanger can also be defined in this way. Okay, so again, knowing the effectiveness of a heat exchanger and then the NTU and C, use the chart to determine U and area of the heat exchanger. Okay, so here we have a parallel flow heat exchanger. Okay, so this graph or this chart gives us the effectiveness of the heat exchanger over here, and this is the NTU, number of heat transfer units, and the capacity ratio is given by the red line. So if capacity ratio equals to 0, then we use this line. If capacity ratio is equal to 0.25 or 0.50, so it goes like that, and then up to 1. Okay, so depending on if you know the NTU to be 3, and for example, you know the capacity ratio to be 0.5, all that you do is that you move upward, vertically upwards, up to 0.5, then you move to the left, then you can find your effectiveness of the heat exchanger in this way. Okay. So similar situations have been given, okay, in the chart for different configuration of heat exchanger. You see over here, so we have parallel flow. This is 2 tubes, 1 shell. This again we have cross flow heat exchanger is this. So these are other configurations that are given. Okay, so now calculate the outlet temperature. In order to calculate the outlet temperature of the fluid, we can use this equation. So this equation is nothing. It is coming from Q hot equals to C H, that's the capacity, okay, times delta T. Okay, so where delta T equals to T hot inlet minus T hot outlet. Okay, so similarly, so that if I'm looking for T hot outlet, then I'll use this equation, and it is coming from here. So similarly, Q for the cold equals to C capacity rate for the cold fluid times the temperature difference. Okay, so this gives us also T cold T cold outlet. So T cold inlet minus T cold outlet. Okay, like this. So then let us look at this particular question. We are told a single pass counterflow shell heat exchanger. So single pass flow counterflow heat exchanger is used to cool mercury from 110 to 70, flowing at the rate of this, entering at 30 degrees Celsius and flowing at a rate of 0.2 kilogram per second. Calculate the heat transfer surface area and then the exit temperature of the water if the overall heat transfer coefficient is given. Okay, so here we can use different methods. Here we are only told a counterflow shell and tube. So one shell, one tube. So we could use also Q equals to UA, okay, times delta Tm. This is possible because we have the area of the heat exchanger area over here. If we know U, we know the value for Q, we know delta Tm, then we can easily find the area. Okay, so here, but we'll be restricting ourselves to use the NTU method. So this is the physical view of the heat exchanger. So you see, this temperature is not known. So we can use this equation to determine let's see, the temperature difference. Delta T2 is this, is given by this. So we have the capacity, the heat capacities is given by this. So this corresponds to C minimum. C minimum is this, C maximum is this, and C minimum is this. Okay, so we can determine our capacity ratio, which is 0.61. So now, based on the question, we will determine this is the amount of heat gain. So if we look carefully, we know the temperature at the inlet for the hot, temperature at the outlet for the hot. So we can easily calculate QH. QH is equal to what? That gives us C for the hot times T hot in minus what? T hot out. So if you get this value, this should be equal to QC, which is equal to C, that is the temperature for the cold, okay? So, and sorry, and this is the capacity for the capacity ratio, the heat capacity for the cold times the temperature difference. So the temperature difference now is going to give us the temperature for the cold outlet minus temperature for the cold inlet. So we don't know this one. So if we, let's say we get this to be 30 kilowatt or whatever it is, then we equate it to this. We know T inlet, we know C, then we can easily find the temperature at the outlet. And that's what we did over here. That's what we are doing over here. You see? So now this is the hot side. So this is the energy release. So the negative side indicates it's energy which is given by the hot fluid, okay, to the cold fluid. That's the significance of the negative side. But again, it does not play any big role in this situation. You can leave it whichever way it is. So now our Q maximum is given by this, okay, because we are going to find the effectiveness. Effectiveness equals to Q divided by Q maximum. So we need to determine our Q maximum as well. So that is it. So now the NTU can be determined using a graph, okay? So we know the effectiveness of the heat exchanger, 0.82, and then the capacity ratio also. The capacity ratio is about, capacity ratio, let's see, what was our, yes, 0.61. So with these two information, we know the capacity ratio and then the effectiveness. So capacity ratio is 0.6. So 0.61 will be somewhere here. So you go directly and then move down. So our NTU is 2.7. So now you equate this 2.7 equals to surface area of the heat exchanger, U divided by C minimum. You understand? So now this surface area is given by this. So now to determine the temperature at the outlet for the cold is also using this equation. Okay, so these are different configurations that are available in the literature. Okay, so depending on effectiveness of the heat exchanger can be calculated, okay, using this equation for a double parallel flow situation, counter flow situation also. Okay, this is for a cross flow, single flow, like this. Okay. Again, these are other relations that are available in the literature. Okay, so the NTU can be determined not only by graphical means. You see here we determine the NTU using graphical, using the graph. So, but there are empirical equations also, empirical equations that are available in the literature which can be used to determine the NTU. So effectiveness is this. So the NTU can be determined for using this equation. If you know the effectiveness, you know the capacity ratio, you can find the NTU. Okay, so later on we'll look at the equation, we'll look at questions related to this area. So the final part is the design consideration for heat exchangers. In all heat exchangers, you see, one of the first things we need to talk about, if you want to design, let's say you are an engineer, you are working in the chemical industry, or let's say a power plant industry, and you want to design a heat exchanger, the first thing is, does the company has what is the amount of energy that you want to transfer from the hot fluid to the cold fluid. Let's say, for example, you take a steam power cycle, steam power plant, where you have a condenser. So condensers always, they need the water from the turbine to be cooled down. So what is the amount of energy that need to be cooled down? You need to calculate all this. Okay, so after you have done this calculation, and then you get the amount of heat necessary to be transferred, then what should be the cost? Okay, the cost of the heat exchanger. Does the company have the budget for this? And then the cost of pumping, because the fluid need to flow through so many tubes. So what will be the cost for pumping or the pumping power? Okay, or even if there's a blower or fan like this. So then the next thing is the size consideration, size and then the weight. So we don't need to design a heat exchanger that will cover the whole company. It should be very moderately. So, and the size is very important. And then the type of heat exchanger. Okay, so do we need the cross flow, or let's say parallel flow situations? Okay, so which type of heat exchanger we need? We also need to talk about that. And then the material consideration is also very important in order to know the thermal stress. Okay, so sometimes if you are dealing with a very high temperature heat exchanger, then the thermal stress that is imposed on the material also need to be considered. Okay, so that application of the heat exchangers. Okay, so these are various types. We have oil coolers, fuel oil preheaters, aftercooler steam generators. Okay, so then we have condenser, mainly in the power plant, and boilers like this. So boiler has a very high temperature. You see, boiler. So exceeding, let's say, sometimes 1,100 degrees Celsius. You understand me? So you are talking about very high temperature system. So the thermal stress of the system need to be considered. Okay, so this brings us to the end of this particular lecture. Okay, so the floor is now open for any discussion. If there's any question, anything bothering your mind, please let me know immediately. Okay, so is there any questions so far? Okay, so if there
Test,
is no,
sir.
yes,
I have a question.
yes,
In example 6.1, the
yes.
material resistance is neglected. So my question is
Example,
the
which one?
example 6.1?
Wait. Let me go there. 1 minute. So 6.2 is this. Yes, this one, right?
Yes. At the
Yes,
assumption, the thermal
yes,
resistance is negligible. Uh, okay, my
yes.
question is the calculation in this whole syllabus neglect the resistance of the resistance of the material?
Oh, so it will be mentioned. It will be
Okay.
mentioned, especially in heat exchangers. It will be mentioned that if the thickness, assuming that the thickness is negligible, the thickness of the heat exchanger, you see,
Okay.
negligible thickness. The moment you come across this, then it means that the tube has no, or the thermal resistance of the tube can also be negligible. You understand me?
Okay.
Okay, so the moment they mention that a heat exchanger, okay, in which a fluid is flowing through, has a negligible thickness. And if this is mentioned in the question, then straightforward, then you should know that the thermal resistance is as well neglected. For example, let's say we have a device of this thickness,
Okay.
okay, so in which heat is flowing through it. But if we have a very thin like this, though this number one is going to resist more heat flow compared with number two. This will readily allow the heat to pass through. You understand me? So we are considering a situation like this where the thickness is very thin. So if the thickness is very thin, then it means the heat exchanger will readily allow the heat to flow through it, and the thickness is very small. So in that case, if the thickness is very small, then it means the outer diameter is almost equals to the inner diameter. You understand me? So you have to be careful when you have heat exchanger. Maybe in the next class, we'll discuss some questions related to this and for you to see. Okay.
Okay.
Okay. So any other question?
I have another question.
Okay.
Okay, the basic idea of the heat exchanger is convection. Is it true?
The what?
The basic idea of the heat exchanger, is it
Yes.
the convection?
You mean convection or what? I can't
Is
hear that.
convection the basic idea of the heat exchanger?
Oh, yes. The basic idea of the heat exchanger is to, you know, transfer heat from a hot fluid to a cold fluid. You understand me?
Okay.
And the idea of convection plays a very large role because we are talking about fluids. You understand me? So we have a
Okay.
hot fluid, heat transfer through the fluid will be convection, and heat transfer through the thickness of the heat exchanger will be a condensation situation. You understand me? So the basic concept over here, even if you look into the car radiator. The car radiator is a
Okay.
typical example of a heat exchanger. If you take out the car radiator from your car, immediately you have overheating in your engine. You understand me? So the car radiator, what it does is that it there is water flowing through the engine cylinder. So this water that circulates around the cylinder, it absorbs all the thermal energy from the combustion. Now, this hot water is sent to the, what do you call it? The car radiator. And what the car radiator does is that it allows the fluid to pass through series of tubes. And then the air flows across it. As you are driving, then the air flows across these tubes, and then eventually the fluid is cooled down. And then the fluid is allowed to go through the heat exchanger again. So the basic idea of a heat exchanger is for a cooling process. You understand me? So, but
Oh.
the convection comes into it when you are talking about the engineering design. You understand me? You want to calculate maybe the amount of heat transfer. You want to look at the thermal resistance, how the heat is being, the concept by which the heat is being transferred from either the hot fluid to the cold fluid. You understand me? Okay, so we are not restricting ourselves so much to convection. Convection is just one part of the heat exchanger. It's an application. You understand me? It's a thermal engineering application of the heat exchanger. Okay. So any other question?
So the car radiator is also a heat exchanger.
Yeah, of course.
Oh.
It's a cross flow heat exchanger. So it's a
Oh.
cross flow heat exchanger because the car radiator has a series of, let's say, so it's a typical example. So in all car radiators, they have what we call flat tubes like this. So I'll say flat tubes. So my drawing is not so good. So they have flat tubes. All car radiators have what we call flat tubes. And in between these flat tubes, we have fins. Fins is embedded in between the flat tubes, like this. So that the hot water, which is coming from the engine, it flows into this. It is distributed into the flat tube, like this. So as it flows down, then the air will be coming with high velocity. See, so this will be like perpendicular. So this fluid is moving downwards, and then we have the air, the cold air is also moving in this direction. So it cools down the fluid. So now the fluid will be collected somewhere over here. Then it goes to the engine again. So a car radiator is a very high example, typical example of a heat exchanger. If you take out the car radiator from your engine, again, you have overheating, and then eventually the car can be damaged like this. So I've had this experience before. So one day I was driving through the highway. Suddenly I didn't know what was happening. Oh, before I realized my car that did already got damaged. And then the temperature rose very sharp, very high. So suddenly, and then I just stopped. And then the car almost got bent out. You understand me? So car radiators are very important. And then also in a steam power cycle where we have, what do you call it? Condenser. The condenser is also an example of a heat exchanger. Okay, in the aerospace. Okay, so all these things they have and the application of heat exchanger is widely used even within our own human anatomy. So the moment you get you run or you walk very fast, you start sweating. So if you don't release the heat energy within you to the surrounding, you will not feel comfortable. Again, you have to exchange heat with relative to the surrounding. Okay, so this is also another form of heat transfer. You understand me? So heat exchanger is a very widely used in the industry. Okay, and like this. Even your motorcycle is the same. Okay. Okay, so is there any other question? Yes, any other question?
No,
Okay,
that's all.
so if there is no question, then I think, inshallah, we will stop over here.